Hello, my name's Ashley Back, and I'm going to tell you about NOVA's latest three-flavor neutrino oscillation results. So NOVA is a long baseline neutrino oscillation experiment with a near detector about 100 meters underground at Fermilab near Chicago, and then a far detector on the surface right up close to the Canadian border in Ash River in northern Minnesota. Both detectors are positioned about 14 milliradians off-axis from the beam, which gives a narrow energy spectrum, peaked at the energy which optimizes electron-neutrino appearance. NOVA is seeking to answer some key questions in neutrino physics. The first one being whether theta-23 is maximal, i.e. exactly 45 degrees, or if not, which octant is it in. Is the electron flavor associated most with heavy or lighter mass states? Or in other words, do we have the so-called normal hierarchy or ordering, as shown on the left here, or the inverted hierarchy or ordering in the mass states, as shown on the right? Is there CP violation in the lepton sector? And if so, what value does delta CP take? All of these parameters that we've discussed so far are encoded in the PM&S matrix, which governs mixing between neutrino flavor and mass states. And this leads us to our last question, which is whether there is physics beyond the standard model and our current view of the PM&S matrix. For example, mixing with more than 3 flavors or other non-standard interactions. We can probe the first two of the parameters we just discussed, the octant of theta-23 and the value of delta m squared, with a simple NuMI disappearance experiment. The NuMI survival probability is given by the formula shown, and you can see it's sensitive to both of those parameters. If we look at the predicted NuMI distribution at NOVA's far detector to what we expect and compare that in purple with what we expect to see in the absence of oscillations, the distribution in red, we can take the ratio of these two predictions, and the distance to the dip gives you a measurement of delta m squared, and then the size of the dip in the ratio between the two distributions gives you sensitivity to theta-23. But to resolve the mass hierarchy and to probe values of delta CP, you need two other things. So first we want to look at NuMI appearance in a NuMI beam. And then second, we need a beam that can run both in neutrino and antineutrino beam modes. And I'll show you how this works now. So if you plot the probability of electron antineutrino appearance here on the y-axis against the probability of electron neutrino appearance on the x-axis, the effect of the hierarchy gives you a slight, the inverted hierarchy gives you a slight suppression in both probabilities. So we get this splitting along the diagonal here between the two hierarchies. Now if we trace out, if we cycle through values of delta CP, this has the opposite effect for each hierarchy, and so we end up tracing out an ellipses in opposite directions. For both of these effects so far, we've only considered oscillations in a vacuum. But if we now add in matter effects, this causes a splitting of the two ellipses along the diagonal because it causes opposite effects in neutrinos and antineutrinos. And then finally, for the octant of theta-23, this causes either a suppression or an enhancement, depending on which octant you're in. So we get another splitting, forming two pairs of ellipses, one for each octant on either side of maximal. So now we know we need a beam running in both neutrino and antineutrino modes. So how do we produce that beam? Well, the NuMI beam at Fermilab starts with a proton beam impinging on a graphite target. And this produces mostly charged pions that then decay into our neutrinos. We charge select the pions to produce a 96% pure beam of muon neutrinos, and then by reversing the horn current on these focusing horns, we can produce an 83% pure beam of muon antineutrinos. The data for the analysis I'm going to present is collected up to March 2020, and we collected 13.6 times 10 to the 20 protons on target in neutrino beam mode. That's shown in the orange here in this weakly accumulated POT plot. And then in antineutrino beam mode, we collected 12.5 times 10 to the 20 protons on target, as shown in the blue weakly accumulated POT points. Once we have our beam, we can then detect our neutrinos with our detectors. So both NOVA detectors are formed with orthogonal layers of PVC cells filled with liquid scintillator for full 3D reconstruction. The narrow cells give us very high granularity, and PVC, being a lightweight material, gives us a very high active mass in our detector. Inside each cell is a loop of wavelength shifting fiber, which collects scintillation light and directs it to the edges of the cell, where it's spread out by an avalanche photodiode. Each cell readout forms a pixel in event displays, as shown here for NuMu and NuE charged current and neutral current topology, event topologies. And the image-like nature of these event views makes them excellent candidates for using deep learning techniques to classify events. NOVA uses a convolutional neural network based on image recognition algorithms to classify events. And then we combine this with basic quality and containment cuts, the precise timing of the NuMi beam, and a boosted decision tree trained on for rejecting cosmics to then select our final neutrino candidates. Now we know how to select our neutrino candidates in data. We need to build a prediction for what we expect to see. So this starts with a simulation of the neutrino flux using J-on-4 simulations, which are then reweighted according to external NuMi beam measurements. So we convolve this with the oscillation probability to get a neutrino flux at the far detector. We then also have to convolve this with our interaction model. So NOVA simulates interactions using Gini 3.0.6 with a custom configuration and tuned to NOVA near detector data and external data. And this update to Gini was a major update in this 2020 analysis. We then also have to do one final convolution with our detector response. So we simulate final state particles propagating through the light collection and read out to the front electronics. And this is again simulated with J-on-4 and was also an update for this analysis. We can use our near detector data to then constrain the far detector prediction. So as we fit our simulation to near detector data, the shifts to the simulation are propagated through the convolutions we just discussed to make adjustments to the far detector prediction. The fit to near detector NuMu data, shown on the left here, constrains our far detector signal, while the fit to NuE data, the near detector shown on the right here, can then constrain our prediction for beam backgrounds. So what did we see in the 2020 dataset? Well, here I'm showing selected NuMu candidates in the black data points, along with the prediction at the best fit shown in purple, and the expected backgrounds to the prediction shown in gray. And so I'm showing neutrino beam mode at the top and antineutrino beam mode underneath. And so we observed 211 NuMu candidates in neutrino beam mode with a prediction of 214.1 on a background of 8.2. And then in antineutrino beam mode, we observed 105 NuMu candidates with a prediction of 105.4 signal events on a background of 2.1. And now looking at selected NuE candidates, again, here I'm showing far detector data, selected candidates in the black data points, and the best fit prediction in the purple. We observed 82 candidates in neutrino beam mode again on the top, and 33 candidates in antineutrino beam mode. The largest contribution to the background, you can see here, comes from the total beam background. So that's whether it's neutrinos or antineutrinos, electron antineutrinos in the beam. We only see small contribution from the wrong sign component and cosmics. And this measurement of 33 electron antineutrino candidates constitutes greater than 4 sigma evidence of electron antineutrino appearance in a muon neutrino beam. So once we have our 4 datasets, we can then fit them simultaneously to extract the values for the relevant oscillation parameters. In the fit, we float 50 individual systematic uncertainties as pool terms, and we correct the significances with the Feldman-Cousins unified approach. So we can look at the fit in contours of delta m squared and sine squared theta 23, and you can see NOVA is in good agreement with other long baseline and atmospheric neutrino experiments in the field. NOVA's best fit point, this black dot here, sits slightly away from maximal with a 1.1 sigma preference for non-maximal mixing. Sticking with the comparison to T2K, we can also look, just comparing to T2K, in contours of sine squared theta 23 and delta CP. And so you can see, if you look at the preferred regions for NOVA and T2K, you can see there's some clear tension between NOVA and T2K in the normal ordering. And then slightly better agreement between the preferred regions in the inverted ordering. To properly understand the agreement or disagreement between the 2 experiments, we need a joint fit to data from the 2 experiments. And this is already underway, and we'll probably quantify this. But to better understand NOVA's best fit results by themselves, we can look at the asymmetry between the 2 beam modes. So we're returning to the ellipses that we looked at before, but this time we're plotting, instead of probabilities, the actual number of observed events in neutrino beam mode and antineutrino beam mode. So you can see NOVA's data point from the observed event counts ends up right in the center of the ellipses. And this means we see no strong asymmetry in appearance rates between the 2 beam modes. And if we plot the asymmetry as shown in the plot down here as well, you can see NOVA's data is consistent both with slightly negative and slightly positive asymmetries. And we can look at what this means in a different plot by plotting the hierarchy and octant combinations as a function of values of delta CP along the x-axis here. And you can see that NOVA's best fit point in the center then disfavors the combinations that are on the extreme points of the ellipses. So we exclude the inverted hierarchy at pi by 2 at greater than 3 sigma on this extreme point of the ellipses here, and the disfavor the normal hierarchy at delta of 3 pi by 2 at around 2 sigma. So looking ahead, NOVA will continue taking data until 2026, ending up with equal exposures in both beam modes. And taking into account the expected improvements to the NuMI beam, and also assuming favorable values for the oscillation parameters, we could see greater than 3 sigma sensitivity to resolving the neutrino mass hierarchy for around 30 to 50% of values of delta CP. We could also see greater than 2 sigma sensitivity to resolving delta CP itself. And NOVA's ongoing test beam program will also help to reduce our detector systematics. So hopefully I've convinced you that NOVA is well suited to investigating key questions in neutrino physics, and will continue to do so as we run through to 2026. Thank you for listening.